population cohorts can get quite complicated. Consider the following case where we're going to restrict mating and reproduction. This is an unusual example that I learned about in the old text by Leuenberger. This is modeling a particular caste system that is recorded to have been in place in a particular American Indian tribe, the Natchez tribe. And here's the way it worked. Society was divided into 4 castes. These were rank ordered. There was a highest, next highest, and then the lowest caste. And there were a number of rules for marriage and reproduction based on this system. Here are the rules. 1. If you are not in the lowest caste, then you must marry someone from that lowest caste. 2. All offspring from that marriage are in the higher of either the mother's caste or one lower than the father's caste. So you compute those 2 things and take the higher one, and that's the caste of the children. Okay, well, that's kind of a weird system, but let's think about it. Let's label these 4 different castes from highest to lowest, A, B, C, D. So A is the highest, D is the lowest. Then what are the rules? Well, assuming the usual binary pairing between a mother and a father, the father could be from one of 4 castes, A, B, C, D. The mother can be from one of 4 castes, A, B, C, D. But most of those pairings are restricted. So A with B, or B with C, or C with B, or any of those things. Most of those are gone because you have to pair with someone from the lowest caste if you are not in the lowest caste. Now, doing so, if you have children, what caste are they in? That second rule, where you are the highest of either the mother's caste or the father's caste plus 1, means that the castes of the children follow the table as presented here. Okay, that's what the rules say. Let's take them and build a population cohort model. Now, this is going to get kind of complicated, so the first thing we're going to do is simplify. Let's start with a simpler 3-caste system. So our castes are now A, B, and C, C being the lowest, and we can build a reproduction table just as before that outlines the permissible pairings and the castes of the offspring of such pairings. Now our model is going to have some assumptions. Let's say that XA, XB, and XC are the population sizes. But to be precise, this is really going to be the size of the number of females in the population. Or, if you like, the size of the number of males in the population. We're going to assume that it's a 50-50 split. That's going to be important later. Remember that assumption. We're going to assume that there's no intergenerational mixing, that everybody pairs up, a whole bunch of things that maybe they're not entirely realistic, but, we've got to do something for a model. And what we're going to do is use discrete time, where the passage of time now means you're going from one generation to the next generation. Okay, so here's our model on these 3 different population sizes, XA, XB, XC. XA at time n plus 1 equals what? Well, how do you get caste A children? The only way to get it is to have a caste A mother. So that means we can take XA at time n times lambda, some reproduction rate. Where here we're interpreting XA at time n as the number of caste A mothers. Okay, that's simple, no problem. But what happens when we look at XB at time n plus 1? Now there are 2 ways to get a child in caste B. One comes from a pairing of a caste C mother with a caste A father. So what that contributes is lambda times XA at time n, where now this XA is the number of fathers. But the other way you can get it is by looking at caste B mothers paired up with caste C fathers. And using the number of mothers, that gives us a term of the form lambda times xb at time n. Now notice here how we're using this symmetry to go back and forth between thinking of these population sizes as the number of mothers versus the number of fathers. Okay, last term, and this is the complicated one. Modeling xc at time n plus 1 gives us what? Well, notice there are two ways to get caste C offspring. One of them involves having a caste C mother with a caste B father. And this is the only way that a caste B father can produce offspring. You see that column where it has a C and nothing else? So one of the terms in xcn plus 1 is lambda, that reproduction rate, times xb at time n. But now for the other caste C term, that column now has other stuff in it. A caste C father can produce children of any caste, depending on that of the mother. So for this last term, what we need to do is take lambda times quantity xc at time n, subtracting off xa at time n and xb at time n to account for the number of caste C fathers that pair up with the caste C mother. And that is it. That is our system. And what kind of system is it? Well, it's a linear system. This is great. I'm going to stack into a population vector p at time n these three subpopulation sizes, xa, xb, xc, and then my system is ep equals some matrix lambda 0, 0, lambda, lambda 0, minus lambda 0, lambda times p. Now if I call that matrix A, I can think of it as a rescaling by lambda of what? Well, I've got 1, 0, 0, 1, 1, 0, negative 1, 0, 1. That's really an identity matrix plus something that's got a lot of zeros in it and a minus 1. That does not look good. That worries me a little bit. And you would be right to worry if you check that when you solve this linear system, when you take powers of this matrix A, what do you get? A to the n is lambda to the n times the matrix 1, 0, 0, n, 1, 0, negative n, 0, 1. Uh-oh. That negative n in that lower right-hand corner, that is not good. Because if I apply this matrix to a vector of initial population sizes, p naught, I get lambda to the n times what? xa at time 0. Then the b population size is n times xa at time 0 plus xb at time 0. That's cool. But the c population size is xc at time 0 minus n times xa at time 0. Oh no, that is not good. That means that eventually our C population goes negative. We have run out of people in that lowest caste. And since everyone has to marry someone from that caste, you can see why this is bad news. So what now? We're sorry? We ran out of people? What do we do? Well, you might wonder, does this happen in the 4-caste version, the more complicated version that we simplified? Yes, it does happen in that version as well. You might also wonder, what happened in practice? This was supposedly based on an American Indian tribe. What happened as generations went on and on and on? And of course, they did not go on and on. Well, let's consider this as a mathematical problem. How would you solve this problem if you could control these populations? If you could control their reproduction, what would you do to fix it?